So welcome to my talk, what classes we design and how, and I need to rush a little bit. For those of you who intend to follow me, and here you can actually see the slides that I'm where they are. For download, I'll leave that on a couple of seconds for you to take a picture with your phone if you intend to. And if you don't find it quickly, go to GitHub, look for my name, and then you will find it under Talks Public somewhere. Now let me get you there. So what is actually what I want to talk about? I want to give you something to think about when you actually design classes. And if you consider types in C++, an instance of a type is a C++ object. That's terminology, at least used in the standard. There are many uses of the term object. And I figured out, okay, give people some guideline to think about what objects they actually create when they work with them. And the most prominent thing to think about is actually values. Everything with respect to values works more or less right out of the box when you use C++. So what is actually a value? We will look into that, what's behind the concept of a value and what's behind the concept of value semantics in C++. We will then go on to further things that you can think about, like what is a subject? And I use the term subject here in contrast to object, just because object is already overloaded and subject might be something else. And with subject, it's important where it is or that it has a location. So it has a here. The value location is completely irrelevant. And to get to a subject, you would follow a relationship. And that's given by a reference or a pointer or some other type that has the relation semantics. This is about where is something. And I will give you some introduction what that actually means, what you can make from having a relation to, as an represented as an object, a relation to another object, what that actually allows you to do. And there's some specific things that comes with class design in C++. Those are the manager objects. These are one of my pet peeves, and I like to explain them a lot, and they will come up in this talk as well. Now let's start. What is a value? There's one nice sentence I stole from Kevin Henney. He was citing Michael Jackson, which is actually not the pop singer, but a person who was a Brit who was writing a lot about software engineering and system analysis. And he's saying a value is an intangible individual that exists out of time and space and is not subject to change. So a value is a value. What does that actually mean? We will look at that in a second. But there's also something Scott Meyers taught us. It's when in doubt, do as the ints do. Integers are the, let's say, the canonical values. Some maybe even say they are God-given and everything is mathematicians and human invention. So int is actually, if you take the number 42, it is a value, regardless how you represent that. So what does it mean that outside time and space of values? The value is the same value regardless of its representation. Considering the number 42, in C++, we have 4 different ways to spell a literal that has this value. And regardless how you spell the literal, the behavior of the value is exactly the same. There's no difference if you write hex 2a or octal 5.2. I hope I didn't make any mistake, or decimal 42. And this is all the same value. So you see, it's irrelevant how you spell it. And the behavior of that value, like, oh, I add 1 and I get 43, for example, as its behavior. This is something that's independent of its location and where it is. Wherever you write 42 plus 1, the result will be 43 in C++, regardless where you compute that. And the most important thing about a value is it exists without the need of other things surrounding it. So if you have a value of 42, it doesn't need some memory on the heap to represent that 42. It doesn't need another object to actually be able to exist or to work with. that is important. It's kind of self-contained, no dependency to others. And we will see what in contrast to that in a second. I have to figure. Now, if you look at value semantics in C++, which are related to values, but more a property of class types. So it's a property of a type. And the major thing in the value semantics in C++ is copyability. You can copy initialize or copy assign a value to another value. And the result is that both values have the same value afterwards. And it's the value of the thing that you copied from. So if you write A equals B, both A and B have the same value, and it is the value of B before it was put into that assignment. And this value semantics is a cornerstone to C++. It makes C++ work, especially that the copy is unchanged. That's an assumption taken almost everywhere, that you can, if you can copy something, the source is actually unchanged. And all the built-in types work like that. They have this kind of value semantics. So if you have a variable of type int and initialize it with 42, it then has the value 42 and works the same as the value of 42 before. Now, what about const? If you make something immutable, it's close to behave like a value. Especially, you cannot change it anymore. So if you assign another object from it, it will have its original, keep its original value. That's guaranteed by const. And there are even some types where you can get value semantics by adding const. For example, a shared pointer of a const type has value semantics. You copy one shared pointer, and if it actually refers to an object, it will ensure that the copy and the original behave identical. But there's one tricky thing. If you add const to a member variable, you lose the ability to assign to an object, which might be intentional, but it can be tricky if you then need to assign anyway. And getting around that limitation by making member variables const is really tricky. On the other hand, there are people who are able to write data types that are completely immutable and still make great software. But this is advanced implementation technique. If you want to learn more about those usages of immutable data that has value semantics, look for Juan Bolivar's CppCon talk from 2017 or his IMA library. And I'm sure he has other talks around that topic as well. So that's not the topic today. Now we have seen values. Values are important. It's built in, and every default in C++ works towards value semantics. Now, it's second row, I said subject. What differs a subject from a value? A subject usually also has a value, but what's more important is it has a location. And this location part is interesting because it allows something very interesting. And identity is important, and the identity becomes important when you look at relation, which is the next thing, and it has a lifetime. A value exists outside of time and space. 42 is always there, but once you put it in a location, it might actually go away when that location is destroyed. So a local variable at the end of a function gives a value a location, and that location might go away. It's usually not a problem unless you make this subject a target of a relation, which we come in general. In general, very often you intentionally make something a subject because it's not copyable. So you must pass it around by a reference or other means that have relation semantics. And this enables us, by having this location part and this relation together, it enables us to get to a situation where we can actually get into polymorphic behavior, which is one of the cornerstones of C++ success, that you can have dynamic polymorphism with virtual member functions. So what actually makes an object a subject is that you actually create a relation to it or enable creating a relation to it. Now, for polymorphic subject types, this is in virtual, we have the mechanics in C++ to have this dynamic polymorphism. And for that to work properly, you must define a destructor in the base class that is virtual, and you want to prevent copy, because copying via the base class then would mean you slice the object at the base class, and that's not what you want to do. There are many details going around with that, and I don't drop into that. I just say what you would do normally, and if you know how to go around that, do so, but have a good reason for doing otherwise. And I will show you how to, let's say, simply define a polymorphic base class in the simplest possible way. Now, let's look at the third thing, relation. I did some interesting forward looking to that. What's a relation? It's always referring to something else. It represents a subject. It does relate to something that has a location, and it enables something that I would like to call Fernwirkung. I use that interesting German word because it's not common to be used in German as well, and also because all the, let's say, translations have so many overloading things like remote control, remote access, that it's very easy to confuse the things. What I'm trying to get with Fernwirkung is actually to allow you to think about, okay, I have access to something that's not local to an expression. So relation objects allow you to change something that's not directly mentioned where you use it, which is kind of interesting. This is actually what Fernwirkung means. You do something and it creates an effect somewhere else that is not directly obvious. And this is an important thing to get in your head, because every time you have Fernwirkung, you have a much need to spend much more brain cycles to actually understand what's going on, and you have to consider a much broader context than when you just write something like 42 plus 1, where there is no Fernwirkung, there's no relation object in that expression, and then nothing bad can happen. It's very obvious what's going on. This Fernwirkung actually allows us to use dynamic polymorphism via a relation object to a subject, where you can have actually the relation object, what it refers to can be a polymorphic base class, and the concrete subject behind that can be one of its derived instance of its derived classes, and thus you have the dynamic dispatch going on. And where are relation objects important? We will see beside the enforced non-copyability of polymorphic base class, there are other situations where copyability might not be achievable or might not be desired. And to actually work with those objects beyond their local expression, you might actually need to employ a relation object to get this Fernwirkung. Now, what does Fernwirkung mean? It's kind of a remote control. You wiggle somewhere and somewhere else, actually something moves, like with the joystick, and it allows you to access or even modify something that is not part of the current expression. And where does that Fernwirkung work? It works for reference parameters, like const reference, where you just access or you can copy something away. It's actually used for optimizing away copies. Instead of copying, you use a const reference to avoid potentially expensive copies. Then you have the L-value reference that are not consts, which allow you to remotely manipulate another object that is not directly partaking in an expression, and the R-value reference that was introduced in C++11, which allows you a transfer of ownership of an object's guts or some other things, but mainly it's for transfer of ownership. And similar things can be said for other types with relation semantics that are relationships like pointers, span, views, or iterators. All these have specific are relation objects. What are technicalities of relation objects? Actually, a relation object cannot exist on its own. A value object always is valid on its own. A relation object is valid depending on the thing it relates to, which is very easy to get wrong. So this is where you actually have to watch out for dangling, for potentially uninitialized relations and other things. And it requires a superhero abilities to actually get that right every time in C++. Other languages give you much more leeway with relation types. There are languages where everything is a relation type, more or less. So the language garbage collector will take care of that. More modern languages like Rust try to keep track of the relations for yourself, so you don't shoot yourself in the foot. But that also requires a lot of discipline so that you are getting things right, but the compiler will help you there. But in C++, you're on your own as a programmer, and you need to employ the right techniques to use relation objects correctly. Otherwise, you can get easily into trouble. Now, how can we get there? The one thing where it's always safe is function parameters, unless the function becomes the starting function of a thread or a coroutine. But let's forget that. For normal functions, using relation types as the function parameter types are safe, because anything that's passed into the function usually remains valid, because the full expression where this object is used is not ended. So function parameters that are relation types are safe. All the other situations require deep scrutiny, if, especially on the context where a function is used. If you return a relation type from a function, you must make sure in the calling code that this wouldn't lead to dangling. And if you put a relation object as a member variable in a class type, that is kind of contagious. If you don't do anything special, your class type now becomes also a relation object. This happened, for example, with standard span, which keeps a pointer to a range, and that pointer easily becomes invalid somewhere else. So span itself, without any, it doesn't have any special management functionality. So it becomes, from having a pointer, it becomes actually a relation type. And there are other kinds of types in C++, the managers that I will introduce soon, that will actually might use a relation type, but in the end will actually make sure that they have the that they don't become a relation object themselves, because they manage the relationship underneath. Now let's have a look at managers. I hope not too many of you have been to my talks about managers before, because there's a kind of a rehearsal of what we have there. What is actually a manager? A manager is something, a class type that manages a single resource, and there are different flavors of managers depending on how hard you try to make this resource behave properly as a C++ type. The first two managers are kind of subject types, so you cannot copy them. They don't have value semantics. A scope manager is used locally to keep something together and manage it again, clean up afterwards. There are some scope managers within the C++ standard library, like, for example, scope block is a scope manager, creating a lock and releasing when it's done, when it's destroyed. There are other situations where you might group objects together and have provide a special access and make sure that they are destroyed when the scope ends. And you would then use a relation to that object as function arguments to pass it down the call chain to actually access this common container of let's say, commonly managed objects. And this is what you would do with the scope manager object. There are unique manager types. The most prominent one, well known from the standard library, is unique pointer, but you might want to do similar things on your own. And these are for resources to be managed that cannot be easily duplicated. Like, for example, you don't want to normally you don't want to copy a heap allocated object around. That's why you use unique pointer, but you want to pass it on somewhere else. And this transfer of ownership is actually what you would implement in a unique manager. And then there are the so-called the general managers. These are the much harder to implement types where you make sure that a resource that otherwise would not be easily be copyable is actually copied, and the general manager takes into account that this resource duplication actually happens when you copy it. And as an optimization aspect, it might implement transfer of ownership on move operations to optimize away the copying when you don't need the copy, but you want to transfer the ownership. But this is just an optimization in contrast to the unique manager, where the move operation is not an optimization, but actually enabling facility of the transfer of ownership semantics. Now, what further technicalities of managers do we have? If how do we detect what is a manager type? A manager type typically is a class that defines a non-empty destructor. It actually defines a destructor that has semantics and does something, a cleanup. So, for example, the destructor of the unique pointer will delete the underlying memory if it's allocated and not null. And usually our managed types have this kind of a resource handle type, which can be a pointer, which can be something else that has relation semantics. It relates to something outside of the manager object itself that is managed by the manager object. It might even be an integer, like a file handle in the situation where you represent an open file with such a manager class, and then that file handle is still something referring something outside of the object, which is more or less the open file descriptor in the operating system that you refer to. And managers care about copying and moving. They might disable all of that, becoming a scope manager, or they might do something else. Something to take home with you: never define a class with an empty body. A destructor for a class where the destructor has an empty body. This is not only confusing, it's also suggesting that you might have forgotten to clean up things, and it's also not obvious why you actually wanted that destructor first in the first place. Unfortunately, some IDEs prefer to generate a destructor for you when you say, I want a new class, and this destructor naturally has an empty body. Don't write code that you don't want to maintain, and don't write empty destructor bodies. And if you find code that has destructors with empty bodies, either delete the destructor completely because the compiler provided one will be there anyway, or in some cases, it might be okay to implement them with equals default, define them with equals default, but don't do empty destructor bodies. And there are some cases where you might have a managing type where the compiler provided destructor is just fine and the manager just cares about copying and moving. I still have to find a very good example where this is reasonable. I've seen example code that shows where you have to care about copying and moving and the destructor is just fine, but this is rare, and most of them were artificial cases or situations where you did some caching or something internal caching of results that you otherwise would have. So the manager actually manages the cache around something else, and I wouldn't go there if you don't need to. So again, summing up, we have the scope manager, which are non-copyable and non-movable. And with C++17 on, we can actually return them from factory functions, which might make, let's say, deducing a concrete type from a template easier to get there, or might even formulate the construction of such a thing easier and not having to spell out its concrete type from a variable definition that you would define locally. Then we have the unique managers that have a move-only semantics and allow the transfer of ownership. And this is for resources that cannot easily be duplicated, but where you actually want to make sure that you are able to transfer the ownership, let's say, for example, down the call chain, which you wouldn't be able to do with the scope manager. It exists where you actually create it. Or you might even want to pass it across a thread boundary to create it from one thread and pass it over to another one. And then there's the general managers, which are where that are copy enabled, that gives you value semantics, and they might have the ability to optimize move, but it's not a necessity. Why I'm talking about all this stuff? Well, I want you to think about if, when you design a class, will it be a value? Will it be a subject, a target of a relation, or will it even be a relation, or will it manage a resource? Or if you combine member variables from these kinds of things into a class, what are the member variables roles? Is the member variable a value? Is it a relation? Is it something where you manage something? And what happens if you combine the managers? For example, if you combine, if you put two unique pointers in a class, this class will become also a unique manager, even if it doesn't define its own destructor, because both unique pointers will clean up afterwards, and it will make the class non-copyable but movable. And this influence gets easily lost when you just look at the technicalities of how a class is implemented, how the member types are implemented. And stating the obvious, for example, if you just combine types with value semantics, your type has value semantics automatically without doing anything special. And if you start from the first principles, oh, what can I do in C++ with class types? Things get easily overwhelming. For example, if you look at what special member functions you might actually have to care about when you consider copying, transfer of ownership, and destruction, and maybe even default construction, you have 6, or let's say 5 or 6 special member functions you need to take care about. Then each of those can be public, protected, or private. It can be not declared, which is the easiest part. Just don't say anything, and the compiler will provide you with something. Or you can define it with equals default, or you can even deliberately define it as deleted, or you might define it with a body that does something. And even then, you might actually end up with then different spellings of potential things. For example, I always start, if I have to define my own assignment operators, I always make them L value qualified. And all move operations should be no except. Otherwise, things get much more tricky. And therefore, I suggest that you think first about the roles, because with these many, I figured even without any kind of special things, you end up with 50 different ways to define your class. And to consciously choose, there are only a few of them that actually make sense, but consciously choosing them and thinking about each of them for every individual of the operations on the left-hand side is really, really hard to get right, especially for beginners. There's even a talk by Howard Hinnant at ACCU 2014, where he takes an hour or so to explain this table, which I don't want to explain to you. Just knowing that table from the top of your heart and considering whenever you actually design a class is really, really hard work, and you don't want to go there, especially since C++ has some dark corners, which are marked red here in the center, that you get copy operations when you actually define one of the other operations like a destructor or other copy operations. And I introduce this table here just to show you later on some specific row in the table that I want to make use of. Now, if you have sub-objects, I already talked about that. This slide tries to summarize. If you have sub-objects, let's say base classes or data members, if everything is a value type, has value semantics, everything is fine. The defaults provided by the compiler just work. And this is what the rule of 0 is about, which we'll see in a couple of minutes. Then if something is a relation type, the relations are kind of contagious. If you have a relation type as a member variable, your class becomes a relation type unless you took specific actions about managing that relationship. If you have a polymorphic base class, it's fine when it's well defined. That means it must be non-copyable and has a virtual destructor. If you have a scope manager as a member, it becomes contagious because it's non-copyable. Your class easily is also non-copyable, which might be okay if you want to combine multiple scope managers to a single thing that go away together, but it's or operate together, but it's usually not that common. You might have a unique manager as a member, and this is when you combine several move-only things together to move them together, which might be okay. But this again is tricky if you must make sure that move operations never fail, otherwise you get into big trouble. It's like trying to manage multiple resources at once. But if you just combine unique managers and values and so on in your class type, your class still is a unique manager in the end that is move only, and it's fine. And general manager, once you've done it correctly and have copy semantics, value semantics by copying things around, using a general manager like a value is fine, and there's no big deal in that. Now, with this conceptual framework, how do we actually define a class? The biggest starter is don't declare any of the special members that we just looked at, destructor or copy and move operations, and let the compiler provide them, and you're just fine. And there are just a few cases where you are not just fine, and these are where we actually consider, and this is where we actually consciously define them. Otherwise, you shouldn't even consider defining them. So why is the rule of zero so good? We can look at the core guidelines. They say, okay, if you can avoid defining default operations, do, and the reason it's the simplest and gives the cleanest semantics. Well, this is a very weak reason. And how do I know if I can avoid defining them? So it's not really helpful. That's why I made this talk or part of this talk, because I want to be more helpful to help you to decide more easily when the rule of zero is just okay. There have been schools of thought that say, okay, I want to see everything. So when you want all the defaults, why not spell them out as all the defaults? So say, okay, if you want the default copy operations, write equals default. If you want the default move operations, write equals default. If you want the defaulted destructor, write equals default. This means you actually define those things, and once they are user-defined, your class type is no longer trivial. It's no longer an aggregate, or you might even get problems with the overload resolution in some specific situations. So that's actually defining the special member functions that the compiler would provide. Even if you attempt to define them exactly as the compiler would provide them, is actually potentially dangerous, or at least potentially changing your code from what the compiler would actually do with it. There are a few exceptions for equals default. One is to resurrect default constructor that might be hidden by otherwise defined constructor, or if you want to define a virtual destructor in a polymorphic base class, because usually you don't want to manage resources in such a polymorphic base class, so you would want a destructor which is behaving as the standard compiler provided one, and this is where you define the virtual destructor as equals default. It's a pity that the C++98 standardization didn't do it that way, but maybe it was decided at the time by Bjarne to not make the destructor of a class with virtual member functions virtual by default for some specific reason that might have broken user code of the first 50 or 100 programs around in C++. I need to check D&E for that. I know it was discussed, but never actually standardized like that. Now, the big question, when does the rule of zero not fit? And I would say the biggest discriminator is when your class needs to define a destructor. There are a few extra cases that you might come up with, but this is the most prominent situation is when your class needs to define a destructor, when you have to do cleanup, or your polymorphic base class then you deviate from the rule of 0. And if you look back in time, this is more or less the cause of Scott Meyers' rule of 3. And most of the time, the actual destructor would be the one that was causing the caring for the copy operations. But this is actually the main reason for looking for defining your classes with caring about the 5 special member functions. There are some odd manager types, as I said, where there's no destructor, but you still have to care about copy and move operations. But I doubt that they are so common, and if they are always a very good idea. Most of the examples I've seen where you have to care about that are arbitrary made up things, or where some specific caching operation that would invalidate the cache when copies actually happen. Now, again, rule of 0 deviation, polymorphic base classes, I already told you. There are 2 rules in the C++ core guidelines that say, okay, the reason is if you delete an object that has virtual member functions via its base class, and the base class destructor is not a virtual member function, then the behavior is undefined. And undefined behavior is something you want to avoid at all costs. And therefore, whenever you have a virtual member function in a base class that you intend to derive from, you make your destructor public and virtual. There are some situations where you want to prevent deletion via base class by making the base class destructor protected and non-virtual. I doubt these are always very good reasons to do so. And because, again, you define a special member functions, which means you lose the implicit move operations by the compiler, and you also lose the provision, a base class with a protected non-virtual destructor. You lose the it's no longer an aggregate, it's no longer trivial, and these are all things that might be problematic. And the second reason why you need to take care about is if you have the default, let's say, potentially wrongly provided default copy operations of a polymorphic base class would actually slice a derived class along the base class, and you want to prevent those slicing copy operations. And this happens, so you want to make sure that a polymorphic base class is not copyable. It's always treated via a relation object and never directly as a value object in your system. Now, how do we prevent copy operations? There are several means to get there. There have been old means in pre-C++11 where you would either have the, okay, I declare copy operations, copy constructor and copy assignment as private and never define them. I make them protected and define them, but they're only usable for subclasses, not automatically by the compiler. I might even inherit the non-copyability by inheriting from boost non-copyable. And C++11 allowed us to define copy operations as the lead. But again, now once we define something, it changes the rules. So while this might be a good idea up front, okay, I don't want copies, so I delete that, and people are recommending that, I think it's not the best way to go there. Because if you want to suppress copying, you have to define your copy constructor, which means you defined one constructor, and looking at our big table, this means your default constructor is no longer provided by the compiler. So to have a default constructor, you now have to resurrect the default constructor by defining it. Deleting the copy assignment operator is not really that bad. It doesn't have any further side effects except that the move operations are gone, which are already gone by the copy constructor. So deleting the copy operation disables the default constructor and disables the move operations. Now, the question is, when you look at that, you have to define 3 things to get there to prevent copying and still behave sanely, or at least 2 of them. Can it be done simpler? And my mantra is less code equals more software. I stole that from Kevin Henney. And the less code you actually write, the less code someone has to review, and the fewer code you have to get your head around. Now, if we look back at at Howard's table, there's one line where it says, okay, if move assignment is actually user declared, even if it's defined as equals delete, this means that there's no move constructor, there is no copy assignment operator, and there's no copy constructor, which means all the bad things have gone, like our class is non-copyable, and we still keep the default constructor because we don't declare actually this constructor, and we will still have the compiler provided default constructor, but the situation where you would do that would actually mean that you have defined your own destructor, because otherwise it usually doesn't make sense to prevent copying of your type. And this thing I nicknamed rule of Desdemona. I didn't come up with a better name. It almost sounds like the woman's name Desdemona, and rule of Desdemona was my feeble attempt to give this trick a name. It's not as commonly known as the rule of 3 or rule of 5 or rule of 0, but I want to make it more prominent because it's the least amount of code to get that non-copyability in your type, unless you use inheritance like with boost non-copyable. And why am I a big fan of it? Because you don't need to resurrect the default constructor. It still remains available. And where is it used? It's used for polymorphic base classes and for scope managers where you don't want to implement or you cannot implement the copy operations, nor move operations. So a polymorphic base class, what we actually do is we have a public virtual destructor that we define as equals default, and we have a move assignment operator that we define as equals delete. The latter can even be defined privately. Regardless, it just ensures that it's neither copy or move operations are applicable. That's the least amount of code to prevent copying, and it's distinct enough to prevent any confusion. And also, it doesn't require any empty body, which is also occurs. Now, that's as much as I want to tell you about polymorphic base class at the moment. And remember, this is the schema to start with. If you really have a good reason to deviate, you may do that. Just think twice before you deviate and have a good reason for deviation. Now, let's look at our managers. How can we implement these managers? Being able to write these manager types is one of the cornerstones of C++, which distinguishes itself from many other languages. The deterministic cleanup and deterministic object lifetime is what we are actually watching out for. Now, destructor is for something called resource acquisition initialization, RAII, or sometimes SBRM, scope-based resource management. It means that the constructor will allocate a resource and the destructor will release it. And those destructors to release it actually will have a body defined that is non-empty. And this is why I hate having empty destructor bodies, because once a destructor body is there, it should actually do some cleanup. Otherwise, the compiler provided one will be just fine. And what I have to warn you about, if you attempt to manage multiple resources with one manager class, don't. I tried. It's really, really tricky. I think I was able to do it for 2 things at once with the unique resource that I proposed for standardization, which is available in the library fundamental TS number 2, and some libraries might have implemented it, but it's really tricky to get right. And I needed help from the biggest brains in the C++ community to get it right, at least to what we now think is correct, but it's so easy to get it wrong. I had so many wrong versions. Don't go there. It's just too tricky, especially for doing it generically. If you want to have multiple things managed, create a manager type for each of individual resource and just combine them together in a bigger class. If you want to have them managed together, then the cleanup, especially if something happens when you allocate one of the resources and it doesn't work, the cleanup will be automatically provided by the compiler and do the right thing. I already showed that slide before, just to sum up: scope managers, unique managers, general managers. Now look at the individual things. The scope manager is the simplest one, and that's even that I would say that, let's say, a normal C++ programmer can easily get right. The thing is, you would need a constructor, which usually would have parameters to actually create something, to acquire the resource, a destructor with a body that releases the resource, and you will prevent copying by the rule of distamova by defining the move assignment operator as deleted. And this is really a schema everybody can follow and which just works out of the box and which helps a lot with keeping resources around. And it's no big deal. That's why I'm no longer a big fan of, let's say, automatic provided scope guards, because it's so easy to write such a type, and you should make clear what you actually manage, that let's say scope guards who clean up afterwards from, let's say, regular code that doesn't wrap it in a type are actually considered, in my opinion, a bad practice at the moment. Write your own scope manager instead of cheating with a finally or whatever you're using for a scope guard. Now, unique manager, we get a little bit more involved because unique manager want to have transfer of ownership. This means you might have a unique manager that has a resource, and another one, once it transfers out the resource is gone. So you need to represent the state of a missing resource, of a non-existent resource. This is easy for pointers. For example, unique pointer just is a null pointer when it doesn't own any memory. But for other resources, it might be more intricate. So you need that extra flag to say, okay, I don't hold a resource. One type that gives us the property of either being something or nothing is standard optional. So a canonical guideline to use your own unique manager is using representing the resource type as an optional of the resource type, so that you can have that extra empty state that you need for a moved from, as a moved from state. And this is in contrast to what libraries assume. When you're using a movable class type, you usually assume nothing about the moved from state. But when you're defining a class type that has move operations where you define them yourself, you better make sure that you know what the moved from state is, because you need to distinguish it when you clean up later on, and as the destructor must know if it has a resource to actually clean up or nothing to do. Now here, because we actually define another constructor, the move constructor, we have to have a default constructor, and it's good to have a default constructor, especially a defaulted one, because with an optional, it will actually create an empty optional is consistent with the moved from state, which is also consistent with other unique manager types like unique pointer. If you just create a unique pointer without make unique, it will be empty and not manage anything. You will have one or more constructors to actually acquire the resource. If that acquirement fails, you must make sure that it's never acquired or either acquired or not. And then there are 3 other operations, which we look at the next slide, where we actually, how those can be implemented canonically. And you see, we have, considering these 5 special member functions we are looking at, we actually have a rule of 3, but it's a new rule of 3 for move-only types. We define 3 operations: the destructor, the move assignment, and the move constructor together. Now, how is actually move helping? This line here is more or less my 1-line explanation how move operations work for a transfer of ownership. You have something with a letter in it, and you assign it to something that is empty. And in the end, the empty part that you assign to has the letter in it now, and the other letterbox is empty. It's actually moved. That's transfer of ownership of the letter. And this is all the magic you need to know. I know others write a few hundred pages on move operations. I think that's not necessary to understand all of that and know everything by heart. If you understand that underlying model, and with the canonical implementation of move transfer of ownership, like I show you here, it's also not that big deal. So what happens in our move constructor, we move the optional from the other thing, which actually moves the underlying resource type. And because that wouldn't clear the optional on the right-hand side, we have to deliberately clear the optional on the moved from to bring it into the moved from state into the empty optional. Similar things happens actually when we have the move assignment, but it's important to prevent self-assignment. Otherwise, you might release the resource that we just moved. So we would end up in my letterbox example with 2 empty letterboxes instead of having the transfer the letter from one letterbox to the other one. So this means we actually check for self-assignment. We release the own resource, so we make the left-hand side letterbox empty if it's not already, and then we swap the two optionals, which just works, and leaves the right-hand side optional in an empty state, and that's it. And for the release operation, we factored that out because this is the same operation we would use in the with the destructor. We first have to check if the optional is actually containing a resource. If it really contains a resource, we have to write code to actually release it, which is omitted here just by a comment. And we have to reset the optional to make it empty. So there's just a fill in the blanks in this line where you actually do your own code. The rest can stay more or less what you are, regardless what kind of resource you want to manage for your type. And last but not least, our well-defined destructor in the body, which is missing the curly brace here because of the rendering. So it just calls release, and this will actually release a resource if necessary, or do nothing if the optional is actually empty. And okay, this is where we go to. Now, I think if you have questions to that code, it's very convenient later if you ask those either in the Gather Town once I get it started again. Now, if we look at the general manager, this is something where you, instead of providing the move operations, you provide the copy operations. To make a resource manager, a general manager with copy operations requires you that the resource is somehow copyable, or you are able to create another resource from the existing resource that behaves the same. It's not about sharing the resource, it's about creating another instance of the resource. And the move operations are only necessary if the duplication of the resource is actually expensive and you want to optimize it away. So for general managers actually defining move operations is only an optimization techniques. And with all optimization, like Don Knuth has told us, premature optimization is the root of all evil or of many evils. And therefore you should actually measure if you really need to support explicit move operations and if it really brings you a benefit. Otherwise, just don't provide them. Copy is sufficient, and a copy operation provided will always be able will fit with the move operation called out for. Another situation where you might not want to implement move operations is actually when you cannot make them no except, which shouldn't be a problem if you, let's say, make the general manager build on the same schema as the unique manager and already have the move operation with the gut stealing, and it's possible to create the copy of the resource, then it's fine to actually implement the move operations similarly to what we had with the unique manager. And what we end up now is here for general managers, we have the classical rule of three: define the destructor, define the copy operation, and the two copy operations. Can you see that? Like that. Or you have the rule of five, where you have the destructor, copy constructor, copy assignment, move constructor, and move assignment, which is the rule of five there. And you will also usually have a default constructor for the general manager as well, with the same rationale as for the unique manager. Now, what you actually get with the general manager, you provide value semantics for a resource which wouldn't have it out of the box. And it's usually expert level coding, and the explicit cleanup might also be a tricky part. And the resource must be copyable or replicable. And very often you have in the standard library already existing types that provide a lot of resource management, especially when it's about memory. So you might actually employ those instead of implementing your own general managers. Nevertheless, if you're really an advanced C++ user and know what you're doing and the resource is copyable or is duplicable, then I don't want to hold you back to implement your own general manager types. Just make sure that you know what you're doing. It's definitely not a C++ 101 topic to get it right. Now, what have we looked at? For the roles, what is my takeaway? Whenever you create a type, make it a value type, unless you deliberately don't want or cannot make it a value type. Just combining value types is so much easier, and everything just works out of the box. You need to deviate from value semantics only for polymorphic base types, or if you actually need a scoped or a unique manager, or don't want the hassle to implement a general manager, or the resource actually is not easily duplicable, or you want to prevent duplication because it's really, really expensive to duplicate the resource. And otherwise, whenever you make something a subject because you create a relation object to it, handle them with care. Everything is fine with relation types as the function parameters, but whenever return a relation type, or even when you have a local variable of a relation type, you have to make sure that the target object outlives the relation type. Otherwise, you will get into trouble. And this is really one of the big things where C++ types is not yet very helpful. So this is actually where programmer brains are still highly recommended to be active when you write code using relationship types. And this is one of the reasons why I usually don't teach pointers to my first, because those are so error prone, even though people feel great when they master them and then apply them everywhere. Pointers are relation types and they have their evil, and especially because they have these many meanings in C++ which we want to get rid of. And looking at the other, what did I talk about? Special members, rule of zero rules. Just don't provide your own versions of copy and move operations or destructors unless you must. And you now know you only need to do them when you actually define a constructor for a class. And never define a destructor, rule of zero, unless you need to define a destructor for your class, and never define a destructor with an empty body. Never. Refactor your code, delete your code, your empty destructors from your code base, or make them equals default if they are defined virtual. That's what I just said. And remember the three kinds of managers: very easy scope managers, a little bit more involved unique managers, tricky part, general managers. So rule of destiny mover for non-copyable types, so for polymorphic bases, and scope managers. Rule of three, the new one with the move operations for transfer of ownership for unique managers, and the rule of three classic with the copy operations, or the rule of 5-6 for general managers. And I hurried up because I started late, even if I were told that we can overshoot. I can talk a little bit about what was missing from this talk, from the basics, how to cope with relation objects. I talked, be careful, be a firefighter, be a superhero, watch out that they can potentially dangle, and dangling is that gives you the dang and bang and explosions and whatever. And this is the big problem in C++ that's not solvable by the type system as far as I understand today. And it's also, having these relationship types is also a big benefit of C++ because it allows speed, you prevent copying, it allows Fernwirkung, so you can actually have remote effects somewhere else, which is sometimes important. It allows references that gives you access to the guts of an object, which is also okay, unless the object is a temporary and you use a reference when the temporary is gone. Again, I'm on the edge to see the use of the keyword virtual in user-defined class types a potential problem, or actually a misuse of the language, because a lot of uses of virtual actually can better be served by other means of implementing dynamic polymorphism. One option is variant, where when you have a fixed set of variations and not an open set like you get with a virtual base class, in a base class, then variant might be a better solution, especially if the different cases have similar sizes. So the variant isn't, let's say, getting a size from one very big one and has many small variants. And this allows value semantics and dynamic dispatching by visiting. It might even get better to use variant in the future when the language evolves like some people would like it to evolve. There's also another trick where you still use virtual and heap memory for your objects, but still your own types remain value types, and you can combine them together. Sean Parent has a very nice talk on that a couple of years ago. I forgot its title, but it more or less employs the envelope letter pattern, where you actually have a manager class that allows to manage the very different, let's say, different instances of different types, and using internal virtual base class with virtual members instead of an external that you would inherit from. And I think I'm ready for Q&A, and I don't have any Q&A on that. Therefore, I stick with that slide and for you to make things. And I think I'm good right now. And are there any questions?